meet the principal axis, these rays are known as, this point where it is meeting is called focal point. So this is what focal point is. It is another definition that is related to curved surface areas and interaction of two mediums. I hope you keep this in mind. Now that we know a little bit about curved surface interactions and focal points, let us now derive the curved surface formula. So how you are going to relate image distance, object distance, radius of curvature with your refractive indexes of both the mediums. So you have this certain curved surface which is convex. This is, let's say this is the denser medium, or let's say this is a medium whose refractive index is N2. This is another medium whose refractive index is N1. We have a point object O, or any object that is placed at point O. Pay attention to the laser point. And we have this point O. A light ray is incident on the curved surface at point A. So you have a light ray which is incident at point A. Then you have the normal which passes through C. And the angle that the normal makes with the incident ray is θ1. Now you have from point A, the refracted ray is going to start. It's going to bend towards the normal and it's going to intersect the principal axis at point I. So let's say this is one ray. The second ray, let it pass undeviated through the principal axis. Right? We have already studied this ray. So now the rays meet at this point. So they intersect at this point. So there is going to be the image here. We know. So let this point be called I. So we have two rays. They are intersecting at point I. So the image is going to be formed at point I. The angle that the refracted ray is going to make with this normal is θ2. This is the angle. The name is written here, but this is the angle, θ2. So now concentrate on θ1, concentrate on θ2. So now we have the angle of incidence, we have the angle of refraction, we have pole, we have center of curvature, we have the point at which they were incident, we have object, we have N, which is the perpendicular drawn from point A. Now let's go further. We have, I told you, center of curvature, image, object, θ1, θ2. Now observe this triangle ANO, this particular triangle ANO. The angle that is formed from incident ray and principal axis is angle alpha. You see. Now the angle which is formed with the normal and the principal axis is beta. The refracted ray and the principal axis form an angle of gamma. What are we trying to do is trying to relate these angles with the image distance and object distance. What is the object distance? You know that distances are measured from the pole. So PO is going to be your object distance, while PI is going to be image distance. While PC is going to be your radius of curvature. This is center. This is the point at which it is coming at the surface of this curved surface or perimeter of this curved surface. So this is your radius PC. PI is your image distance. PO is your object distance. Now try and observe the triangle ANO and ACN. You have angles alpha and angles beta. So there is one bigger triangle you can see, which is triangle AOC. This is the triangle you have to concentrate on, A, O and C. This contains both angles alpha and beta. This is beta, this is alpha. Now we have a property of triangles which state that the sum of the two interior angles is equal to the opposite exterior angle. This is the exterior angle, θ1. So θ1 is equal to sum of two interior angles, which is alpha plus beta. So in triangle AOC we have alpha plus beta, which is equal to θ1. Here is θ1. So that is your first equation, remember that. Now we will relate this triangle. Triangle ACI, that is formed by normal, refracted ray and part of principal axis. Right now we have incident ray, we had normal, and we had principal axis. Now we are having refracted ray, principal axis, and normal. So you have theta 2, you have gamma, and you have beta. Same principle we are going to apply, and we are going to take out the value of theta 2. So theta 2 plus gamma is going to be beta, because theta 2 and gamma are two interior angles, the sum of which is going to be beta. So beta is equal to theta 2 plus gamma, or theta 2 is equal to beta minus gamma. You just get that. So in the triangle, we have beta equal to theta 2 plus gamma. So from here you can say theta 2 is equal to beta minus gamma. So now you have theta 1 and now you have theta 2. Both of them are angle of incidences and angle of refraction. From Snell's law of refraction, you have n1 multiplied by sine of theta 1 equal to n2 multiplied by sine of theta 2. This is Snell's law of refraction, right? So you have n1 multiplied by sine of this angle equal to n2 multiplied by sine of this angle, which is theta 2. Now we already know that theta 1 is alpha plus beta and theta 2 is beta minus gamma, right? We have already made them. These are written here if you focus on the red laser. Here is theta 2 and here is theta 1. So let's now substitute the values of theta 1 and theta 2 in alpha and beta, in the terms of alpha beta and beta gamma. So what you will get is n1 sine theta 1, which is n1 sine alpha plus beta, equal to n2 sine theta 2, which is beta minus gamma. Here it is written on the top. Now what happens is, you will study something called paraxial approximation in later classes. When the rays are moving very close to the principal axis, the rays can be treated as parallel rays, and these are called paraxial rays. The angles alpha, beta and gamma, they become very small, and the approximation of sine alpha plus beta is equal to alpha plus beta only. So what happens is, this sine alpha plus beta actually becomes the sum of the two angles. The value of this particular trigonometric ratio, sine alpha plus beta, becomes alpha plus beta, while sine beta minus gamma becomes beta minus gamma only. So now this approximation leads us to sine alpha plus beta, which is here in our equation. It becomes alpha plus beta, and sine beta minus gamma becomes beta minus gamma. So you will substitute these values in the equation 1. So now you will get n1 multiplied by alpha plus beta equal to n2 multiplied by beta minus gamma. Here is the equation. You just substituted these values over here. And now you can just multiply and say n1 alpha plus n1 beta equal to n2 beta minus n2 gamma, which is your second equation. Now since all angles are very small, I told you sine alpha plus beta becomes alpha plus beta, sine beta minus gamma becomes beta minus gamma, just the value. So now you can take out tan alpha also. You know tan is the trigonometric ratio which is perpendicular divided by base. So you have tan alpha in this triangle AOP, or AON actually. AON is the triangle where you see this is the right angle triangle. So in the right angle triangle, tan alpha is going to be AN divided by NO. So tan alpha also is going to be only alpha. So tan alpha equal to alpha. Why? Because the angles are very small. So you can approximate tan alpha to be equal to just alpha. So tan alpha is equal to just alpha, which is equal to AN by NO. That is what is written here. Similarly, tan beta in triangle ANC, beta is going to be AN by NC. In triangle ANI, see this bigger triangle ANI where I is an acute angle and this is the right angle that we will take. Tan gamma is going to be AN by NI. And that tan gamma is going to just become gamma. So we have alpha, beta, gamma values. Now these alpha, beta, gamma values are what you can substitute in equation 2, where you got n1 alpha plus n1 beta equal to n2 beta minus n2 gamma. You have n1, n2, now you have the values of alpha, beta and gamma. But you have them in AN and NC and not actually from P. So what happens here is, You substitute the values of alpha, beta plus gamma in equation n1 alpha plus n1 beta equal to n2 beta minus n2 gamma. You get this equation. What happens is, observe this particular diagram. In real cases where this aperture is very small, n is actually very close to p, and since n is very close to p, they both basically coincide, or you can say that they are very close to each other that you cannot differentiate which one is n and which one is p. So n and p are coinciding, so they are at the same one point. So an is similar to ap, or an is basically ap. So what you can do is, instead of an you can write ap everywhere, and instead of pc you can write nc, you can write pc, instead of ni you can write pi, and instead of NO over here you can write PO, because N and P are coinciding. So after you substitute these values, you will get N1 by PO plus N1 by PC equal to N2 by PC minus N2 by PI. And now what is PO? Our PO is object distance. From the pole, this is object. What is PI? PI is our image distance, which is from P to I. And what is PC? It is our radius of curvature. So if you get this, you get N1 by PO plus N2 by PI gives you N2 minus N1 by PC. If you take both which have PC as denominator on one side, you will get N2 minus N1 by PC. So this is the equation that you get, which shows you the relation between the refractive indexes of two media and the object distance, image distance, and radius of curvature. What you have to do is find the angles. From the angles, you have to find the angles which contain your sides of object distance, image distance, and radius of curvature. Once you relate them and you approximate them, you can find this equation. The above equation is true for the case that we have considered. And now to substitute the values of PO, PI, and PC, we will need to use sign convention. Sign convention is important, where it will be negative, where it will be positive. So for all purpose of applications of refraction at curved surfaces, be it lenses, be it the curved surfaces we are discussing, and even through lenses, the sign convention is used. So before we get to this equation, remember N1 by PO plus N2 by PI gives you N2 minus N1 by PC. This now, before substituting the values of U, V, and R, let us first discuss the sign conventions that are used. For all purpose of applications of refraction at curved surfaces through lenses, the following sign conventions are used. All distance will be measured from the pole or the optical center. Here, once you come through lenses, you will see that this point will become origin or O. We will discuss about this later. Right now, this point, this is the point from which you will measure all distances. Next, distances measured along the incident ray will be positive. Distance measured opposite to direction of incident light are negative. Heights vertically above are positive and vertically down are negative. So this is the direction of incident ray, let's say the vertically right hand side. So that will be positive. And vertically horizontally right hand side will be positive. Horizontally left hand side will be negative. So if you are measuring object distance, it will be minus U. If you are measuring image distance, it will be plus V. If you are measuring the radius, it will be plus R. So if you take them and if you substitute them, PO is minus U. As we discussed, object that images or distances which are opposite in direction of incident light. This is your incident ray going in the right hand side direction. So now if you have to take the distance, it is opposite, right? PO. So from P to O, it is opposite to your incident light, and hence it is minus U. PI is in this direction, in the direction of incident ray. So it is positive V. PC is also in the direction of incident ray. It is plus R. If you substitute this in this equation that we formed earlier, you will get N2 by V minus N1 by U gives you N2 minus N1 by R, and this is your curved surface formula for refraction. If you were to relate the object distance, image distance, and radius of curvature with the two refractive indices of the media that is given to you, you will use this particular formula. It is valid for all cases. So PO is object distance, PI is image distance, PC is radius of curvature. According to sign convention, you substitute the values and you get this particular equation. This is the derivation of curved surface formula for image formation. Let's go further. Now, since we have the curved surface formula for the particular refractive indices, we will now study what lenses are. So let's say you have two spheres. One is here. Let's say one is this one and one is the other one. You cut a part of a sphere and you cut a part of another sphere. They are two small spheres and now you join them. So this is a part of one sphere, this is a part of a second sphere, and if you join them, let me show you. This is a part of one sphere, this is a part of another sphere. You come and you join these two parts of spheres, and what is going to be formed is going to be a double convex lens. This is bulging outside, this is bulging outside, and hence we have a biconvex lens. So a lens is basically formed when two transparent materials, a transparent materials which is bounded by two surfaces. This is the transparent material, or this is the transparent material, this grayish area. They're bounded by two surfaces, if you see. And both surfaces are spherical in this case. So a lens, what a lens is bounded by at least one curved surface. Because if you see here, this is not a curved surface. This is not exactly a curved surface here. So it's one curved surface, one plane surface. Maybe both of them are curved surfaces inwards. Maybe both of them are curved surfaces outwards. So a lens is formed when a transparent material which is bounded by two surfaces, out of which one surface is spherical. That is how when both of them come together, or the object which is formed is termed as lens. Lenses are of various types. If two surfaces which are both outwardly bulging, if they come and form a material, it's called a biconvex lens. A biconvex lens in itself is a convex lens. Biconvex lens are just called convex lens. Then you have plano-convex lens. That is, you have a plane mirror and then you have a convex lens, convex material. So if you have a convex material and if you have a plane material coming together, then you have a plano-convex. If you have a concave material inwardly curving versus joining a convex material, you have a concavo-convex material. Similar for biconcave, plano-concave and convexo-concave. Two inwardly curving materials, if they come and they are joined together, they form biconcave lens. If one plane material and one inwardly curving material, if you join them together, it will form a plano-concave lens. If you join a outwardly curving material which is convex and an inwardly curving material which is concave, then it will form a convexo-concave lens. So these are the lenses which are being formed. Now, these are the lenses which we discussed. Those that have convex as their principal lens will be converging lenses. Those that have concave as their principal lens will be diverging lenses. Now, the terms that are related to lenses: optical center, center of curvature, radius of curvature, principal axis, principal focus, focal length, focal plane, aperture. You have terms relating to lenses. Lenses have different terms, just as we had surfaces for concave, convex. We had some different technical terms that we were using to describe some line segments, some measurements, some points for the lenses. So we have them for mirrors also, we will have them for lenses also. The first one is optical center, second one is center of curvature, then is radius of curvature, principal axis, principal focus, focal length, focal plane, aperture. Let us study all of them one by one. Optical center. This is the lens. There is a certain point on the lens which is the midpoint of the lens, also the origin of it is also called origin. It is true in case of both convex lens and concave lens. This is the point O. This is termed as the center point of a lens. The center point of a lens is represented by O and it is called optical center. Optical center is a point on the lens directed to which incident rays refract without any deviation. So if any ray is passing through the optical center, then that ray will go undeviated. So we have here the optical center acting as the point which will be the normal. So if you draw any ray which will pass through optical center, principal axis ray, any ray which will pass through optical center for lenses, these are now cases of lenses, things will change. We will even discuss the behavior of incident rays here. So the center point of a lens is the optical center. Any ray which is passing through this optical center will go undeviated. Optical center is a point on that lens. Now, center of curvatures. Now you have two imaginary spheres that are making this lens, right? You have one imaginary sphere here and you have one imaginary sphere here. Even in the case of concave lens, this is one imaginary sphere's part and this is one imaginary sphere's part. So both of them will have their different centers of curvatures, right? So in a lens, we have two centers of curvatures. And usually these centers of curvature, usually if they are made of the same material, the distance between O and the first center of curvature and O and the second center of curvature would be same. But if they are made of different material and if they are not convex or biconcave, then these centers will differ. So the centers of these two imaginary spheres of which this lens part and this lens part is a part of, these are center of curvature. So for this sphere, this is the center of curvature, C1. But for this sphere, this is the center of curvature, which is termed as C2, if you see in the diagram. So centers of curvature will be the centers of two imaginary spheres of which the lenses used to be a part of. Since we have two centers of curvature, we will also have two radii. So the radii of two imaginary spheres of which the lenses are a part of are called radii. If you look at this particular part of the lens, which used to be a part of an imaginary sphere, this will have one radii of curvature. If you go from the center to the point, this will be the radii of curvature, first radius. If you look at this particular part, this will have another imaginary sphere, and this is the center of that imaginary sphere. And since this is the center of that imaginary sphere, if you go and draw a line to this point from the center, this will have another radii. So the first center of curvature is represented as C1. It will have radius R1. The second center of curvature is represented as R2 and it will have center of curvature is represented as C2 and it will have radius of curvature R2. The principle of axis is the line that will join C1, O, C2. C1 first center of curvature, optical center origin, then we have C2 that is second center of curvature. Similar for concave lenses, C1 first center of curvature, then we have optical center and then we have second center of curvature. As you can guess, since we have two centers of curvature, we have two radius or two radii, then we also will have two foci. You can call two focuses or two foci would be the right word. So let's go to foci. Before foci, we come to principal axis. You know that the line, that imaginary line that will join your two centers of curvature of the lenses, that will be principal axis of the lens, and principal axis of the lens will also pass through optical center. Then we come to principal focus. As I told you, lens has two principal focus. C1 will have one principal focus and C2 will have one principal focus. First principal focus is a point on the principal axis that the rays starting from or directed to which become parallel after refraction. So this is your first principal focus, that is after the lens. So on the right hand side, that will be your first principal focus. The one behind here, this one, the one on the left hand side, that will be the second principal focus. So first principal focus, second principal focus. Now we have focal length. You know that the distance between the optical center origin and the focal point F will be the focal length, will be represented by letter F. Focal plane. Now this is a plane. If you draw a certain plane that will pass through, through the focus, then that plane will be called focal plane passing through the focus, and it will be perpendicular to principal axis. This is your principal axis. If this is your principal axis, this is the plane that is passing. This, my hand will represent the plane, and this plane which covers the focal point will have the focal plane. This will be called the focal plane. If this is the focal point and this is the plane, then this is the focal plane. Effective diameter of the circular outline, this is the aperture. Effective diameter of the circular outline of the spherical lens is called aperture. It is not the effective diameter of the sphere of which the lens was a part of. It is the effective diameter of this circular outline. This is termed as aperture. Now that we have discussed the behavior, the definitions that were relating to our particular lenses, we have to now come and find out the behavior of certain light rays that are incident on lenses. We have first discussed this behavior of certain light rays that were incident on one curved surface, right? So now, since the lens's aperture is very small, we will show one kind of refraction, or we see that there is this kind of refraction taking place. So there are some rays whose interactions we already know, and those rays will help us form images. So we know that one ray that is parallel to our principal axis, it will go and pass through the focus. One ray which is coming and passing through optical center will go undeviated. So these rays are the rays whose diagrams we will see, after which will help us draw image. The intersection of these rays will help us draw image diagrams for both concave lenses and convex lenses. So first one, rays which are parallel to principal axis after refraction will pass through principal focus in case of convex lens and appear to be coming from principal focus in case of concave lens. So if you see in the diagram that is given to you right now, this is the convex lens and this is the concave lens. Here is the ray coming parallel to principal axis. After refraction, it will go and pass through the f2. This is principal focus. It will not pass here, it will pass through f2. And you have to first draw the parallel ray, then you have to show refraction and you have to show that it is passing through f2. So before you do this, you have to draw the lens. You have to draw f1, f2. If you want, you can draw c1, c2 and mention radius of curvature, focal point also. It is good to have good labelings. Second way, when the ray is traveling again to parallel axis, you know after refraction, it will diverge. This is a concave lens, it's a diverging lens. So after refraction from the center, optical center, if you see, refract the ray and it will go away from this normal. Since it is going away from the normal, if you bring it back, if you extend it back, you will see that it will appear to be coming from f1. Since it will appear to be coming from f1, you can say that the refracted ray is coming from f1. So both cases. Anyway, if ray is parallel to principal axis, after refraction, it will pass through principal focus of the convex lens or appear to be coming from the principal focus of the concave lens. So the principal focus of the convex lens is the second one, but the principal focus of the concave lens is the first one. Now, the second behavior of light. First, we studied that light ray was parallel to your principal axis and after reflection was passing through principal focus, or after refraction was passing through principal focus, or appeared to be coming from principal focus in case of concave mirror. Now, for simplification purposes, what we are going to do is represent our convex lens, because they are very small lenses. The aperture is very small. You can represent convex lenses as double arrows, if you see in the figure, and you can represent concave lenses as double Ys. So convex lenses will be represented as double arrows and concave lenses will be represented as double Ys. Just to show similarity between the fact that this is a convex lens and this is a concave lens. Okay, so now we have The first case, where rays of light are directed through the focus, or they are appearing to be coming from the focus. Let's see both of them. First case, in the case of convex lens, we have the rays of light, they are appearing from the focus. So if they are appearing from the focus, after refraction, they will become parallel to principal axis. So from you draw the incident rays from f2, which is principal focus of convex lens, and here you will have a certain ray of light. It will be incident on the lens at a certain angle. After refraction, it will become parallel to principal axis. Every ray that is passing through focus after refraction will become parallel to principal axis. This is the case of convex lens. Now come to concave lens. You see that the incident ray is incident on the concave lens at a certain angle. But if you are extending that ray backward, you see that it is appearing to be coming from the principal focus. It is not coming from the principal focus. It is appearing to come from the principal focus. So what will happen to these rays also? After refraction, they will become parallel to principal axis. After refraction, they become parallel to principal axis. So if you are drawing an incident ray in the direction of the focus, you know that immediately after refraction, they will become parallel to principal axis. Even if you don't draw these dotted lines, you know that you're drawing an incident ray in the direction of the focus. So after refraction, they have to become parallel to principal axis. So if you extend them, you see that they are coming from the they are coming from the focus of the concave lens. This is the diagrammatic representation of both of those ray diagrams, where ray is either passing through the focus or either it is directed towards the focus. This ray, incident ray, you see this is directed towards the focus. It's not really coming from the focus, it is coming from some source light. It is incident on the concave lens at some angle, but it is directed towards the focus, means its intent is towards the focus. But after refraction, it will become parallel to principal axis. Let's go to the next one. Rays passing through the optical center. We have discussed this before. In case of either convex lens or in case of concave lens, in both cases, if you are drawing a ray which is passing through the optical center or origin or O, it will go undeviated. If it is passing through optical center O, it will go undeviated. There is absolutely no change, because your optical center will now have the point which contains the normal. So the angle of incidence is 0. Hence, they go undeviated. This also, they go undeviated. Absolutely no change in the direction. So rays directed through optical center will emerge out undeviated. So here is the lens. Here is the incident ray at point O. After emergence, it goes on in the same direction. It goes on in the same direction. Next. Behavior of light when ray is passing along principal axis. Principal axis, if it is passing along, you know it's going to cross O. And since it's going to cross O, the angle of emergence is 0. The ray is directed towards O, it will go undeviated. The ray is directed towards O, it's going to go undeviated. This is true in case of both, in case of your convex lens and in case of your concave lens. If you want, you can draw the basic lenses also, where we have this. Instead of, you can draw these also. I'm sorry for the bad diagram. You can draw this lens also, but the point is, when you are refracting here, you have to refract from the middle. This is the lens. This is point O. You have to refract from the middle. This is parallel to principal axis. After refraction, it will go in some line. But drawing this is way more difficult than drawing this. For simplification purposes, you can use this. So you have a certain convex lens, let's say it is like this. This is center O, let's say, and a line that is going just passing will pass through and will keep passing through. So here, this is so small that you don't have to consider what is happening inside here and why refraction is not taking place twice. The aperture is very small for us to consider the fact that the refraction has to take place twice. It it indeed will, but these are too close to each other, they are very small, and hence for simplification purposes we only take refraction once, and that too from the middle, right from the middle. If you are drawing this diagram, you will refract your ray right when your ray is here. So if you have a certain ray which is parallel to principal axis, then it's coming here, it will come till here, that is the middle, and then it will refract from the middle. So to avoid all this, basically you take arrows for simplification purposes. You don't have to go through this, you don't have to take the middle of the lens and then refract the ray from the middle of the lens. You can just directly do this. So that is it. These are the four light rays whose behavior we are going to check when we are going to see image formation by both convex lenses and concave lenses. So this was all for this session. I hope the basic curved surface formula and how which of the rays we will be using for both image formation by convex and concave lenses is clear. So sign convention, let's discuss it again. For all purposes, for the application of refraction, we will take all distances will be measured from the pole or from the